All right, we've got our list. As a reminder, just let me know if you want to add anything to this list as we go. Another reminder for our friends on the camera, STEM Center Thursday before lecture. Go practice with Johnny and Sagan, and any questions that they can't answer, bring them to our last day of review on Thursday. We covered it in like the last 15 minutes of class. Yeah. Want to go in depth? We can review them for sure. That'd be good. Okay, I say we start off with the practice final and just get that pulled up right away and get that out of the way, and then we'll go from there into the maybe our midterm, and we'll look at our midterm. Question 4 on the practice final. Which best describes the substituent in the starting material? What's the name of that starting material? Bromobenzene. So bromine, all of our halogens, they fall into their own unique class on our aromatic substitution reactions. I guess, actually, one way that we need to tackle this problem, this was your question, Russ? One thing we need to know to tackle this problem is, are we looking at EAS versus are we looking at NAS? So I guess now might actually just be a good time to just do a review of the components of EAS and NAS. Then we'll come back and actually have an answer for this problem. What does EAS stand for? Good. Electrophilic aromatic substitution. You know how we call SN1 and SN2 our first order nucleophilic substitution? So we could actually call this SEAR. It's substitution electrophilic on an aromatic ring. Maddie, if you have anything you want to add to our list today or Thursday, just let me know when we get done with something and I'll put it on the list, okay?
Real quick,
Topics we're going to cover, yep. Okay, so EAS, this is where the ring behaves as what? The ring is the nucleophile because it is substituting itself with an electrophile. It's going to attack the electrophile. NAS, nucleophilic aromatic substitution, which we said earlier in the semester we can also call SNAR. Again, the ring is substituted by a nucleophile, which means the ring behaves as what? Electrophile. Let's go back to EAS. What types of groups will activate the ring to be a nucleophile? Activators will activate the ring. And in this case, these are electron donating groups. Activate the ring. Can you explain that? Can you tell me why? To do what with?
To attract so the electron can grab.
If the ring is a nucleophile, it needs electrons to do that. So it will gather electrons from the donating groups and use those electrons. And I say gather, right? But we're talking about this magnetic push. Electrons are being donated by the electron donating groups, and it creates a better nucleophile. In terms of NAS, what types of groups activate the ring to be a better electrophile? Electron withdrawing groups activate the ring. This is the biggest issue, is that most of our time in this chapter, we looked at EAS reactions. So you guys got to know electron donating groups as activators and electron or orthopara directors a lot. But that's just in the context of EAS.
So when you say the word activate, that means giving it either electrophilic character or nucleophilic character.
Whatever it needs for the reaction that's proceeding. Yeah?
So we're taking it from neutral and we're going to one side or the other for whatever the reaction is.
Correct. Where you've got benzene. If you need benzene to be an electrophile, you'll activate that by having a group that takes electrons away from benzene, puts a larger partial positive to be a better electrophile. If you want the ring to be a nucleophile, have a group that gives electron density to give it a more partial negative to be a better nucleophile. All right, then electron withdrawing groups for EAS would be deactivators, and electron donating groups on NAS. I use the word inhibit. Some people think that that means like, oh, that just slows it down. So maybe we should use a different word. They forbid. Is that weird? They don't just deactivate the ring. They forbid NAS from happening. Inhibit is the word that I would rather use, but prevent. Thank you guys. That is a good word. And then remember, halogens play a different role in all of these groups. Halogens also deactivate a ring for EAS, but halogens are the leaving group for NAS. I worry that I may be asking you to cram some things together here because there's actually some good pieces of information that we could sprinkle in to what we've just made. Electron donating groups for EAS are orthopara directors. Electron withdrawing groups, despite the fact that they make it harder for the ring to do EAS, they can still be present, but if they are the major director, they will direct the next group meta to themselves. They destabilize the intermediate if the group is orthopara. So the easiest way is if the group is added meta. And halo groups are orthopara directors. So the halo group is a combination of electron withdrawal, electron donor. They are a unique group. And that's because those halides are large. They have a strong electronegativity, but their polarizability pulls electrons away from the ring, so the ring cannot donate electrons as well. But in the intermediate, they can share electrons to form a new resonance form, which stabilizes the intermediate orthopara. So they are a unique group. In NAS reactions, electron withdrawing groups are orthopara directors. It wouldn't really matter what the EDG group is, but it might be interesting, or it might be useful to know that alkyl groups don't prevent this. Oxygen groups, nitrogen groups, those will prevent NAS reactions. Alkyl groups actually won't prevent NAS. And I don't know if there's anything else to say about the halogens. Maybe an interesting thing here would be to say that F is the best leaving group, which is strange because C to F is the strongest bond, which means the rate determining step here is not about bond breaking between the halogen and the carbon. The rate determining step is about breaking aromaticity. And F creates the largest partial positive on the carbon, making it as easy as possible to break aromaticity. Anything else you guys want to add to this?
Can you just draw the groups and the electrons going to the orthoparamedic solution?
Can you phrase that a different way for me?
You would describe it as resonance of the EW, EWG, and EDG.
Yes, we're going to look at resonance forms in a little bit. That's what you want to get to? What about reactions that fit into these categories? Where is alkylation, adding an alkyl group? Sorry? EAS, alkylation. Where is acylation? EAS. Where is sulfonation? EAS. Where is nitration? EAS. Where is bromination and chlorination? EAS. I think that was it. So what the hell is NAS? We don't have any names for it. That's where you have a nitrogen nucleophile, like NR2 minus acts as a strong nucleophile. Or you have an oxygen nucleophile, RO minus acts as a nucleophile. There's no names for it though. Kind of like how there's no name for the SN1 and SN2 reactions in OChem 1. And I have an issue with that because SN1 and SN2 are just too broad of names to make it make sense for the diversity of different chemicals that can be in there. And it's the same with SNAR. It doesn't have a specific name. You recognize it by the reagents. All of the named reactions are EAS. NAS doesn't have any named reaction. Anything else you guys want to add in that overview of EAS and NAS?
So if the alkyl groups don't prevent NAS, are they like neutral or do they promote it? Or just like
This is where the nucleophile is drawn. The nucleophile attacks the carbon bonded to the halogen group.
except alkyl?
Oh, I'm sorry, I thought you said halogen.
No.
Do they what?
I was just asking, are they like have a neutral effect?
They're still deactivators. So they're still opposite of how they played a role in EAS. They still deactivate the ring. They would be meta director, but that doesn't like, they're not, kind of in the same way that EWGs are not actively directing, they're kind of like, if you go another way, you're going to be more destabilized. It's the same with the alkyl groups. It would just be a higher energy intermediate. But generally, you're going to have an electron withdrawing group, and that will be the major director. All right, we needed this background because this question says, which best describes the substituent in the starting material? And then it has combinations of activator, deactivator, orthopara-director, meta-director. We need to know what type of reaction is happening. Can you name the reaction that's happening in that step 1? Alkylation, which is EAS. So how is bromine described in EAS? Deactivator, orthopara-director. How is the alkyl group described in that second step? First of all, what's happening in that second step? NAS. Can't name it anything unless you want to call it something like hydroxylation, right? I don't have any better name if it's an RO minus group, and I don't have a better name if it's a nitrogen group. So we're having NAS in the next group. How does that alkyl group behave? How does it impact the ring? It would be a deactivator, and we might call it a meta-director, but there's no other bromine to go to, so it doesn't really matter. Sorry, ignore that. We've got lots of stuff going on with Gen Chem classes this week. Russ, did that answer your question on this?
Yeah, I think so. meta is neighboring. Am I remembering that right?
Nope. Ortho, meta, para. How do you guys remember that?
Ortho is right next to it. Meta is an M, so you turn outside and it's just a
Okay.
And then para like parallel.
Did you like orthodontist? Ortho, meta. What? How did you do para?
Parallel.
Parallel. Para means around. But like paralegal? Are those related? Go around legals? Go around the ring. It's on the opposite side. I guess there is a connection there.
And then the middle.
Or just remember and that's your order. Ortho, meta, para. I think when you say ortho, meta, para enough times in that sequence, it becomes second nature to just say ortho, meta, para. And at that point, you know the order. Adjacent, 1 to 3, 1 to 2, 1 to 3, 1 to 4.
So here's D.
Deactivator, ortho, para, director, D. Okay. Were there other questions from the practice final? I don't think there were. So let's go back. Oh no, let's take this time that we're on EAS to answer this other question about the resonance forms. Okay, here's the challenge with the resonance forms, and I believe it was the resonance forms of EAS and NAS where I finally started bringing in worksheets. And I think that worksheet might have been the worst worksheet I brought in all semester because it was a first effort. But you guys will remember that I tried to give you several different scenarios of EAS and NAS with different combinations of ortho-para director, meta director, what type of reaction is happening, because there's a lot of combinations. So, Jacob, was this your question? Whose was EAS? Yeah. Is there anything in specific you want to see about the resonance forms?
It's just kind of knowing. So my main problem is just the oxygen.
Mm. Okay. So if you guys are okay with this, I say we look at a few instances. I'm going to give the starting material and the reactant so that we know what type of intermediate we're going to look at. So let's look at this compound. Can anyone name that? Yes, phenol. Also, hydroxybenzene. And supposedly benzenol. And let's do an acylation reaction. I'm not going to show the mechanism here. We can come back and review some of these mechanisms if you guys would like to. But I'm going to skip a few, show the resonance forms. How does this alcohol group direct the ring to be a nucleophile? Ortho-para. Does it matter whether we show the ortho substituted product or the para substituted product? No, it does not matter. We will have the same number of resonance forms, and the oxygen will stabilize the resonance forms in exactly the same way. It's just structural isomerism as to where the acyl group will be. So, for sake of convenience of drawing, let's put it para. Here's an issue. That carbon that the acyl group is connected to is sp3 hybridized. And bond line structure says we can assume that hydrogen. And it will make an ass out of you and me if we do. So let's show it so that we know for a fact we cannot put a double bond to that carbon. Now, the positive charge is going to be on both carbons surrounding it at some point. So we can start with our resonance form having the positive charge on one or the other carbon. It doesn't matter. Let's just put it on the left, and we'll show our resonance forms moving clockwise. Is this the most stable resonance form? Sorry, did I say minus? It's a positive charge in the intermediate because the ring has donated electrons to an electrophile. There should be a positive charge. Is this the most stable? Do you know, or do we need to draw more to be able to determine it? Interesting. I want you to know right now that this is not the most stable. That's why oxygen is the director. Oxygen will stabilize this intermediate at some point, and we're going to show that. All right, let's get electrons from the adjacent pi bond to satisfy that carbocation. We're going to move the carbocation to the position that holds the oxygen. Notice how right now the oxygen is poised to be able to share a lone pair with that carbocation. What has my electron donating group just done? Wow, what a good name for it, right? Our electron donating group has now donated electrons, stabilized the ring. Why is this the most stable resonance form? It is not because of charge. The most electronegative atom does not want a positive charge, correct? The least electronegative atom wants a positive charge. This maximizes octets. Another way of looking at that is we have maximized all of carbon's bonds. Carbon has maximum number of bonds. Because when carbon lacks a bond, unless it has a lone pair, then it has lacking an octet. I don't know if it's about energy. I mean, it's about valence shells, so I guess that is energy. Our last resonance form, oxygen gets its electrons back, and this other pi bond in the ring moves its electrons over. Remember at the beginning, I said it wouldn't matter which carbon we started with. Both carbons on either side of this substitution position will hold that positive charge.
When we're talking about maxing out our octets, that really applies to carbon most.
It's almost always carbon. In fact, boron does not want an octet because that maximizes charge, which is why we start with minimize charge, then maximize octets. If minimizing charge means not maximizing octets, that's what you want to do for boron. But for carbon, you need to maximize bonds in order to maximize octets. Unless carbon has a lone pair, in which case you don't want that negative charge on carbon, and so then you'd get to the third rule, which is put the negative charge on a more electronegative atom. All right, I do want to show you guys an idea that I have. I might even phrase this on the final, but I don't know. I don't want to throw you guys off. Oh, you won't have to draw these on the final, so you'll never have to show these mechanisms again. You will likely see a problem, a multiple choice problem that asks you about intermediates during the reaction. Which of the following is not an intermediate during the reaction shown above? So you still need to know how the mechanism works to understand how the reaction proceeds. But I'm thinking in the future to ask my students not to show arrow pushing to all of the resonance forms, but to show arrow pushing simply to the most the most stable resonance form. To get to this resonance form, I would simply show the pi bond from the correct position attacking my electrophile. But if I wanted to get directly to that most stable resonance form, once again, no resonance forms exist. They're make-believe, like Santa Claus. Oh, what a bad time of year for me to spoil that for you. Which means that all of those resonance forms, any of those resonance forms, could be shown forming at this initial step. So what arrows would I need to show the formation of that most stable resonance form straight away? Do you see what bonds need to be made? Do you see what bonds need to break? Oxygen still shares its lone pair, much like it did in this resonance form. The top pi bond needs to come over, much like it did in this second resonance form. And the correct pi bond still needs to attack, just like it did in our initial mechanism. I'm just combining the arrows of the resonance forms into the arrow of the initial attack, because resonance forms all exist at the same time. So if I'm just showing arrows in a resonance form, I can show that in a nucleophilic attack. And here you notice that the oxygen is donating in the mechanism. So I am considering, when I teach this class again in the spring, not having students show mechanisms where they draw all resonance forms, but where they show mechanisms to show the most stable resonance form. That's right. Esterification mechanisms, acetal mechanisms, and condensation mechanisms. No, I think I'm going to give you aldol condensation and Claisen condensation mechanisms. Huh? And I should have removed it. You guys might have noticed, you didn't notice because you don't get to see each other's quizzes, but I had aldol addition on the unit test, aldol condensation on the unit test, and Claisen condensation on the unit test. And I tried to make sure that they were all the same number of steps. But obviously aldol addition is within aldol condensation, so they can't be the same number of steps. So I required aldol addition mechanisms to show all resonance forms of the enolate, and aldol condensation didn't have to show all resonance forms, which was a bad way of doing it. So I wish I'd gone in there and removed some of those problems, but ultimately the submissions were pretty good. What other thoughts do you guys have on this mechanism? Well, then the last step of the mechanism is deprotonation. In this case, the catalyst has bonded to a chlorine, and that chlorine will use its electrons to deprotonate and reform aromaticity. Where? Definitely not. Aluminum, actually just like boron, because they're in the same family, aluminum prefers 3 bonds. That's having 4 bonds, that's too many. Okay. Good review, or do you want to see another? Oh, you were kind of interested in the nitro groups too. How about we do this analysis? Instead of showing all the resonance forms of one mechanism. Sure. And let's show like let's show the nitration reaction. Which of my two substituents will direct my new nitro group? The methyl will direct the new nitro because the nitro group is deactivating the ring and the methyl group is slightly activating the ring. The methyl group is the weakest activator, but it is activating. How will the methyl group direct the new nitro? Ortho or para. Good. Doesn't matter which one we show because both structural isomers are possible. So any preference? Then I say we make it easy again and we add it para to the methyl group. Once again, we'll do this 1, 2, skip a few. Meaning I'm not showing the formation of the activated electrophile and I'm not showing the nucleophilic attack. But the para carbon will attack and then I'll have some other bonds in here.
That's a question on
Yeah.
why the nitro group, is it just that it's such a relatively small meta-directing effect that the alkyl group will just completely take over and it doesn't even matter that there is some meta-directing?
It actually comes down to the energy of the intermediates as predicted by the functional groups. So let's say that we were just doing this with nitrobenzene. And let's consider the energy of the 3 possible intermediates. When the nitro group acts as a ortho-para director, the energy is the same. And that's because there is a very destabilized resonance form where the carbocation ends up on the same carbon that the nitro group is on. The nitro group, as a withdrawing group, already creates a very strong partial positive on that carbon. So doubling up a positive charge on top of that partial positive destabilizes the ring. And a similar resonance form exists when the nitro group when the reaction occurs ortho to the nitro group. A similar resonance form exists. So this is simply very destabilized. When the nitro group has a substituent added meta to itself, the positive charge will never end up on the carbon that has the nitro group. It'll bounce around that carbon and the positive charge will never land on it. So this is just less bad. However, the methyl group, by comparison, if we had just toluene, the methyl group actually stabilizes that positive charge. Oops, can't do that. By holding the carbocation on a tertiary carbon. So essentially, I know I've separated it to say nitro and toluene, but essentially, the nitro group cannot stabilize the intermediate, but it can destabilize aggressively or destabilize partially. Whereas the methyl group can actually stabilize the intermediate. So you're asking, should I have nitro direct and go to this high energy intermediate, or should I have methyl direct and go to this low energy intermediate? What will happen? It will go to the lowest energy intermediate. In the event that the nitro group and the methyl group kind of agree with their alignment, which actually happens here. The new group is being added it's being added meta to the existing nitro group, which means that this nitro group will never destabilize aggressively. So this new group is both para to the methyl and meta to the nitro, which seems to agree with how they both direct. It has nothing to do with the nitro group, and it has everything to do with the methyl group. It's like, this is the analogy that always just seems to work for me. It's like an employer that has a really good employee who's productive and hardworking and a really bad employee who's lazy and doesn't do the jobs well. When the employer comes in and both employees are working and a job is finished and done well, who do you think the employer credits for that job well done? The strong, hardworking, the one that has always been reliable to make things happen. Maybe I do need to work on that analogy, but that's just because both of them could have been the director doesn't mean they both contributed something to the reason it directed that way. Does that make sense? So we say the strongest activator is the one that lowers the transition state the most, and that's why it is the activator, or that's why it is the director, because it provides for the lowest stability, the lowest energy, the highest stability. All right, so resonance forms. We should find that the resonance form never sits on the carbon with the nitro group, because that would destabilize, and it's meta to the nitro group. And we should find there's a resonance form that has a tertiary carbocation. Here's my tertiary carbocation. And you'll notice that that carbocation is going to skip a carbon. It will never land on the carbon with the nitro group. Otherwise, it would destabilize it more. But that got offset by this stabilizing resonance form. And Jordan, did that answer your question enough? Or is there anything left that I can try to touch on? Okay, so that's where we're going to get into the NAS resonance form. And that's where our electron withdrawing groups actually play a role. It's pretty much exactly the same resonance structures. You'll notice that positive charge never sat on an ortho carbon. So the only thing that would change is that this ortho carbon would be the sp3 hybridized carbon, and it would never be part of a pi bond. But the positive charges would still sit here, here, and here. The positive charges will sit on the same positions. No, this one only has 3 resonance forms because the electron donating group can't actually donate electrons. It has no lone pair to donate. Oxygen had a lone pair that it could push into the ring. Nitrogens have a lone pair to push into the ring. The carbon is donating what? I like to call it moral support. Yeah? It's sitting there with electron density. Hyperconjugation, which is all of the surrounding hydrogens that it has, their bonding electrons are helping to fill in that p orbital, that empty p orbital. So they are stabilizing by hyperconjugation. If that was a nitrogen group instead of methyl, now there's a 4th resonance form. Good. All right, let's look at the resonance forms that come from NAS. I always need a leaving group on NAS. And it's useful to have an electron withdrawing group on NAS. And when it comes to my reagents, there'll just be some strong nucleophile, some negatively charged nitrogen, some negatively charged oxygen. And in this case, actually, there is no preparation. So the reason that I was doing this 1, 2, skip a few on my mechanisms is because I didn't want to show the creation of the electrophile. But NAS doesn't need anything to get ready. It's ready to go. So instead of showing a circle, I'm actually going to show you how these electrons will move. And so while we're at it, let's just show the formation of the most stable resonance form. So I'm going to take my tosylate group and I'm going to draw it out so that I can show how the electron withdrawing group engages in the NAS reaction. And yes, yeah. Imagine that well, we can show it too in a little bit. So nitrogen here acts as a nucleophile. The biggest partial positive is where the halogen is. So the nucleophile donates electrons there. That means the pi bond at that carbon breaks over. This forces the next pi bond to break, and it's going to move towards the sulfur. Sulfur being more electronegative and larger will pull the electrons towards itself. And this will break open one of the SO pi bonds. Notice how the electron withdrawing group has pulled electrons out of the ring. The nucleophile donated electrons, and the electron withdrawing group has pulled them out. Again, this is not how I showed you the mechanisms earlier in the semester, because I showed you just break one bond at a time, then show a resonance form, then show a resonance form. You don't have to. You can show the formation of any resonance form, and this is forming the most stable. A little complicated? Sure, but not impossible, and truly the most plausible. Now, Killian, to your question, if this was a nitro group instead, the nitro group has a very interesting structure. It's already a Zwitter ion. And some of you brought up a very good point during the semester, which said that this resonance form doesn't look like the most stable resonance form because it doesn't seem to minimize charges, whereas the resonance form where we actually abbreviate NO2 does seem to minimize charge. It looks like there's no charge on the left and 3 charges on the right. But there are charges in NO2. It's just hidden by the abbreviation. The reason that this is the major resonance form, oxygen holds the negative charge. The reason that this is the most stable resonance form, oxygen holds the negative charge. Was that what you were looking for? Good. The nitro group, the sulfonyl group, the carbonyl are electron withdrawing groups. They only hold the electrons during NAS, when there is an excess of electrons. These groups never hold the electrons during EAS because there aren't electrons to be held. The ring has just gotten rid of them.
Electron withdrawing groups deactivate in NAS?
Let's take a look. Electron withdrawing groups activate NAS. Why? Why do they lower the energy of activation for NAS? They stabilize the resonance form. And this is another diagram that I really need to work on and start bringing to my classes. If we look at the resonance form for bromine to go to this sigma complex, it takes more energy to do this if there's an electron withdrawing group on the ring, but it takes less energy to do this if there's an electron donating group on the ring. And that's a bad example because there's obviously no other group that's been added at my position here. But then the same thing goes in opposite. If we're looking at NAS compared to just benzene, an electron withdrawing group will stabilize the resonance form. And an electron donating group prevents NAS. How does it prevent it? Makes it very, very high energy. So high energy that it might not happen at all. And then you've got these caveats inside of there, which is the electron donating group can really do this if it directs orthopara, because then it can engage with the resonance form and create a new resonance form. And the electron withdrawing group does this rather than this, so long as it doesn't destabilize the ring extra. A lot of nuance to it, isn't it? Okay, should we move on from EAS and NAS? You feel like all of your questions have been answered here? Then, oh, good thing I didn't erase that other page, huh? Because the whole list is on there. Let's go to that question that was on the midterm exam. Let's start talking about ranking. By the way, have you filled out your course evals? Please and thank you. They really help me figure out what's working and what's not working. Obviously, the course evals are anonymous, so you don't have to feel any sort of way about what you submit. And I really appreciate the constructive criticism. I get some criticism that's not constructive. The constructive criticism is super appreciated. All right, question 20. Ranking. I knew that. Okay, this is what we're doing. Let's talk about actually, let's talk about reactivity, since that really segues us. How do you feel your perception of this question has changed after our review of this concept? How do you feel like this question, rank the reactivity of the aromatics by NAS? How has your understanding of that question changed after this review? Has it? We have bromobenzene, para-bromonitrobenzene, para-bromophenol, and meta-bromotoluene. Oh, a good time also for me to remind you, I tend not to take breaks during the review days. So if you need that, to get up and move around, feel free to. But I'm going to try and give you guys as much time as I can during this. What, I just erased it, what is necessary for NAS? The aromatic ring must have what? It must have a leaving group. And that leaving group will be our halogen. So this is ground zero. This is neutral. Everything else will either fall higher in energy or lower in energy than this compound. Does that sound valid? Now we look at the other substituents. Forget about the bromine. That's the leaving group. How does a nitro group change this? How does an alcohol change this? How does a methyl group change this? Notice how this hits on each of the 3 points. Electron donating, except for alkyl, and electron withdrawing. Who wants to explain the rationale here? You said B? Oh. More reactive than A. Good. That's our baseline. The 2 electron donating groups deactivate the ring relative to that baseline. The 1 electron donating group activates the ring relative to that baseline. Well, something always leaves in any substitution reaction. What leaves in EAS? What leaves in electrophilic aromatic substitution? A hydrogen always leaves in EAS because the last step of EAS is deprotonation. So something always leaves in substitution. In NAS, that leaving group is a halogen. Where would you place this compound? Let's call this E. You have an idea? I don't want to put you on the spot. I just thought you were getting ready to speak up. Relative to baseline, how would this substituent affect the reaction? It's an activator. Because it's pulling electrons So you think it's going to show up left of the baseline? Because this is least reactive, right? It should go towards the more reactive, just like this other nitro group. In terms of resonance forms, this meta-substituted electron withdrawing group, as an electron withdrawing group, it is pulling electron density out of the ring and putting a positive charge more in the ring. So it does make it a better electrophile. So we know that E is going to be on this side of the baseline. But as a meta-substituted group, will it be able to engage with the resonance form? Will it actually be able to pull out the negative charge? It can only pull out the negative charge if it's positioned ortho or para. Prove it. Do it for yourself. Put it meta. You'll never be able to form a resonance structure where that meta-substituted group can take it out. You would end up breaking an octet rule. Totally. So when I say you'd never do it, I mean, you could probably do it, but you couldn't do it, you know? So given the fact that it still activates the ring, but it doesn't engage in a resonance form, where does it go? More reactive than B or less reactive than B? Raise your hand for more reactive. Oh, less reactive? If it can't pull out the electrons, that means it can't provide an extra resonance form, and extra resonance always stabilizes. So it's going to be less reactive than B. It's still making the ring a better electrophile, but it's not stabilizing the resonance form. Do I still have my... That is to say, if this is an ortho-para substituted electron withdrawing group, then this would be a meta-substituted electron withdrawing group. Still lowers the energy of activation, but not by as much. All right, how about this structure? Two withdrawing groups, both ortho-para, meaning both will engage in the resonance form, both will create an additional resonance form, stabilizing the intermediate even more. That would be the most reactive. All right, last one. Here, what is this, G? Oh, my G's look weird, huh? Would you guys agree that when we created this ranking line, we spaced out everything evenly, but that's not how they're really reacted? It's like there's a huge gap between C and D. D will actually react. C won't react. So it looks like they're evenly spaced out, but C is way down here. How does this new G compare to C? Roughly equivalent, but with an electron withdrawing group. The donating group will still prevent the reaction from happening. But the electron donating group seems to encourage it a little bit more. So would you say less reactive than C or more reactive than C? More reactive than C. But probably still much less reactive than D. So falling somewhere here. No, I wouldn't say it's impossible. Show me something that's impossible. Someone will do it. Yeah. Mm-hmm.
So it gets to the extremely hard, makes reaction
Yeah, without like decomposing your product or something.
Oh, just doing elimination on the bonds.
No, just like breaking stuff off, having other side.
Ionizing.
Huh?
Ionizing?
Sure, isn't that ionizing? I don't know. I don't have a good answer for you. It's just not something that people explore. All right. We wanted to talk about acidity the next, right? And so I think we'll take the acidity ranking problem, and we'll move on from there to talk about ranking pKa, because almost for sure you'll have a question on the exam that has you rank, and it'll probably have you rank the acidity of alpha carbons. So Christina, I think this was your problem. Was there an aspect about it that you wanted to talk about? Because we're not going to see the ranking of, we probably aren't going to see the ranking of alcohols on the final. Could. But it might be more of a multiple choice question than a ranking problem.
I just remembered in that question, I'm definitely not an A.
I see. So you were totally thrown off by it because you weren't sure how to rank them. Okay. We know that alcohols have a pKa roughly between 15 and 18, which is about the pKa of water because water is an inorganic alcohol. But we know that we can lower the pKa of anything by providing resonance to the conjugate base or to the conjugate acid. Excuse me, don't listen to that. So if I can provide some sort of resonance, oops, this is not the type of resonance I need. Meaning, if that oxygen is connected directly to some sp2 carbon, then its conjugate base can be in resonance with whatever that sp2 hybridized carbon is. So in the example of an enol, the conjugate base is in resonance with the alpha carbon. In the context of phenol, the conjugate base is in resonance with the entire ring. So phenol has a pKa roughly around 10. 5 orders of magnitude more acidic because it can share its negative charge with the ring. Now, if that ring can share that added electron density with an electron withdrawing group, that will drop the acidity even more. Only if that electron withdrawing group really engages with the resonance form, being ortho or para. Boy, you know, now that we talk about it, it seems like resonance forms is the whole semester. Was there anything we didn't involve resonance forms? Yes, the alcohol chapter. That was pretty much it. And this doesn't drop the pKa as much. This will be, I mean, I guess I don't have a good number, between 5 and 10. And what might those electron withdrawing groups be? Nitro, carbonyl, or acyl, and sulfonyl. That means you've got extra forms where oxygen is holding the negative charge, but you also have these forms where carbon is holding the negative charge. So then we get down to our carboxylic acid, and this has a pKa around 5. There's only 2 resonance forms, but the negative charge is split between oxygens. So notice how there are 2 phenols in this problem. how would you compare the acidity of two phenols? We have one alcohol, we have one carboxylic acid, those are going to be our ends. But both of the phenols are in resonance with the ring. What do they have different from each other? Their position relative to what? So saying like its position close to two oxygens, inductive effect. The inductive effect here will not be nearly as strong as the resonance effect. So let's like take off the hydrogen. We'll put in the pi bonds, and we'll see where the electrons can go. They can go here, which means these have to move. Boy, wouldn't it be nice if I could get it into my electron withdrawing group? Wouldn't it be nice if my electron withdrawing group could withdraw the extra electrons from my oxygen? And now when I do the same thing with the other phenol, erase its hydrogen, put a negative charge there, and try to share that negative charge of the other phenol with the electron withdrawing group, form a pi bond, move a pi bond, move a pi bond. Oh, I can't break the octet there, move a pi bond. All I did was resonance inside of the ring. I never actually got that negative charge out of the ring. So the phenol with a specific relationship to the electron withdrawing group has more resonance. Specifically, more resonance with a more electronegative atom. What relationship was needed? Ortho-para. Ortho, here we've got meta, which means it's only my ortho-para relationships that contribute to the resonance forms. And we saw that last time. EAS, an electron donating group, only contributes to resonance, ortho-para. NAS, electron withdrawing group, only relates to resonance when it's ortho-para. And then our electron, our acidity.
So, I guess my question, I gotta figure out what it is, sorry. Does it matter ortho-para more if they go to the two, or are they the same? So if you do the one that is ortho-para, it's because the technically the ortho one is closer. Does that then provide, I guess?
I had an old friend reach out to me this fall, studying for an entrance exam like the MCAT maybe, and asked me to explain the ortho-para effect in acidity. Now I had never heard of it before because we don't talk about it in OChem. I think it's maybe more relevant in biochem. And it says something to the effect of ortho positions are more acidic than para positions because of how the electrons are able to interact with each other. So somehow this proximity actually allows for kind of like an intermolecular interaction, whereas para doesn't allow for that proximity, so you don't get that interaction that further stabilizes. Not a learning objective for our class. So I would never give you one that's ortho, one that's para, and ask you to show which is more acidic. But there is reason to, and I don't know that it's with alcohols. It might have been with some other group. So I don't have a good answer for you there, but you don't have to worry about it.
Is that what we did this last chapter? What is that? Beta?
Well, this doesn't have anything to do with alpha hydrogens being deprotonated.
Stability?
Yeah. Oh, we've been talking about stability and resonance forms since Unit 2. All year. So let's talk about the acidity of alpha hydrogens then, shall we? Because that's the type of ranking you're going to have to do. And again, it comes down predominantly to resonance, maximizing resonance. What? Oh, you want to guess?
So, I'd say
Yeah. Yeah, I didn't do that on purpose. It was 4, 3, 2, 1. Mm-hmm. And you guys actually had my practice midterm, and one of the answers was A, B, C, D. I don't do that intentionally, but it happens, which I guess is kind of a reminder. Like, don't be too suspicious about weird answers on exams. Like, when you start getting C for 6 answers straight, you got to trust your gut at some point. You can't go in there just changing answers because it looks weird. Randomized exams are random, so they have random answers sometimes. Okay, alpha hydrogen acidity. If you guys will bear with me, I'm going to draw a big molecule here. Very big. And I'm going to show the aldehyde. Rank them. No. Yes. Yes, it is. I want you to think what stands out as the most obvious for high and low, and then start applying what you need to about resonance to the rest. And the other things like substitution and induction. Should I bring a fan to this room on our exam day? And like put it in the corner here, and or maybe put it over, I don't know. Well, I'll leave the PowerPoint on for white noise.
Oh,
That's
for
actually white.
noise. Oh.
No, for airflow. I'd bring the fan for airflow. Just worried about how hot it'll get again. This room can get hot. And this is a big class. All right, let's talk. What's on your high end of acidity? I'm sorry if I don't map it the same way that you're going to put it. Let's say most acidic on the right and least acidic on the left. Sorry, most acidic was? D? What is the pKa of that central alpha carbon? Do we remember? Yeah, it's 13. If it were two ketones, it'd be about 11. But because it's between a ketone and an ester, it's less acidic. It's about 13. It's the pKa of a carboxylic acid. Why is it called acid?
That's better.
Good question. D has how many resonance forms? 3. Alpha carbon and both carbonyls. How many resonance forms does phenol have? 4. On the oxygen and on 3 of the carbons. 4 resonance forms didn't beat out the carboxylic acid last time. 3 resonance forms is not beating out the carboxylic acid this time, but you might say the carboxylic acid has 2 resonance forms on 2 oxygens. The central alpha position has 3 resonance forms, 2 of them are on oxygen. Doesn't that mean the same number of oxygens, but even more resonance? Yes, except for where the hydrogen is coming from in the first place. What's easier, taking a hydrogen from a carbon or taking a hydrogen from an oxygen? Why? Oxygen's more electronegative. There's a stronger dipole in the bond between O to H and C to H, regardless of how stabilized the conjugate base is. So the carboxylic acid here is our most acidic hydrogen. True, less resonance forms with the same number of oxygens holding it as D, but it's a more acidic atom. And it's not like it's, well, it is much more acidic. It's like 6 orders of magnitude more acidic. Then D. What is on your least acidic side? A? You seemed a little surprised by that. What would you have said? Did you get there? B as the least acidic? Okay. Any other offers as to what might be the least acidic? E? If you look at my pKa table on Canvas, you'll find that there is not an aldehyde hydrogen listed. I've tried looking into it, and I had a hard time finding an answer. I don't think a lot of people calculate the pKa of aldehydes. So what we do know is that an sp3CH that cannot be involved in any resonance. Can anyone tell me why this conjugate base would not be able to be involved in resonance? No nearby pi bonds. The carbon to the right is sp3, can't engage in resonance. The oxygen to its left has an octet, can't take electrons. So E is just sp3 cannot take electrons, or cannot be involved in resonance. That has a pKa in the 50s to 60s. A is an sp2 hybridized carbon, and generally sp2 hybridized is more acidic than sp3 hybridized. A is also close to an oxygen, so there's a stronger inductive effect. Well, I guess E is also close to an oxygen, isn't it? So simply on the basis of they have similar inductive situations, but difference in hybridization, I'm going to say that E is actually the least acidic and A is slightly more acidic, but I would never give this to you on an exam because I think it would be very hard to predict it without doing a more in-depth study on acidity of aldehyde hydrogens. We should say that they are not acidic, much like E is not acidic. These are not acidic hydrogens, but if they were to be deprotonated by something that strong, they'd probably be pretty close to each other. Okay, now let's try and fill in the gaps. Where will B, C, and F fall? F after A. Why? So F has resonance with the carbonyl, correct? As does C. C has resonance with a carbonyl. As does B. B has resonance with a carbonyl. So B, C, and F are all alpha hydrogens, meaning that they're in resonance with a carbonyl. But the carbonyl they're in resonance with is different. B is in resonance with an aldehyde. C is in resonance with a ketone. F is in resonance with a carboxylic acid, which we didn't consider when we looked at it in class. But the carboxylic acid is closer in relation to the ester. So we could say the acidity of the carboxylic acid's alpha hydrogen should mirror that of the alpha hydrogen of an ester. So F is less acidic than B or C because of its proximity to the ester rather than a ketone or an aldehyde. And how does aldehyde and ketone compare? The aldehyde is more acidic. So we would have C and then B. So this dealt predominantly on induction and didn't have as much to do with substitution, correct? How could we use substitution to secure these positions for C being less acidic and B being more acidic? If you weren't sure about the functional group reactivity, how could you change the substitution of one of those carbons to lock in that sequence? I guess I should point out, would you agree that B and C have the same substitution, which means that their enolate form will have the same alkene substitution? So substitution is not playing a role here. How could we change the substitution to make sure that B stays more acidic? Add a methyl group to it. Make it a tertiary carbon. Now that it's tertiary, the enolate is more substituted, which means that it is now even more acidic than it was before. So 3 impacting factors. Induction, the type of carbonyl plays a role. Substitution, the more stable the enolate, the more stable the enolate. The more stable the alkene, the more stable the enolate. And amount of resonance, which is why we had D as one of the more acidic so early on, because it has the most resonance.
If you have a methyl group there, then that's more substituted. If an H leaves, there's going to be a minus on that methyl group. Won't it hate that?
There is no negative charge on this methyl group. The H leaves from B.
Yeah.
The tertiary carbon.
Yeah, the tertiary carbon will be a minus there.
Yes, not for long though. And in fact, not at all. It's a negative 1/2 charge on the tertiary carbon because a more major resonance form is when oxygen holds the negative charge.
About it, but
Mm.
but I'm always going to be lower on the most. Is that kind of right in the hydrogen? Does that make sense?
Can you say that one more time?
So like if you drew a line between like the D and C, the oxygen, like that, one side will always be on the most, and one side will most likely be more on the least. It's a flip happening. It's not like it's ranked, but you can almost go every time. One part of it is going to be way more than the other half.
While I was grading your unit tests, I started finding myself using this term central alpha carbon or central alpha hydrogen a lot more than I normally do, which is this. It's alpha to 2 carbonyls, so I'm kind of calling it a central alpha carbon. That's I think what you're pointing out. An alpha carbon on the left-hand side is less acidic than an alpha carbon between 2 carbonyls. That central alpha carbon, alpha to 2 carbonyls, always more acidic. Is that what you're asking? Alpha to 1, less acidic. Alpha to 2, more acidic. Okay. And maybe to kind of visualize it, like here is the resonance hybrid for the enolate formed by that aldehyde alpha position. And here is the resonance hybrid for the enolate formed at this central alpha position. You can see that that resonance spans more atoms. So the delocalization is larger. That game of like whack-a-mole, where's the electrons? It gets harder to play. All right. Oh, what can we do in 7 minutes to torch you with? IUPAC?
No.
I think we can. One time I did it in 25 minutes and then they hired me because of it. I didn't do a good job though. I'll be honest, I walked out of that teaching demo interview and I was like, oh, I just gave away my teaching job. I'm not getting hired. There's no way that was the best they saw. And then it took a month and a half for them to get back to me and say, oh, you got it. All right. Let's see. The generic form of a name contains the prefix, the root, the locant, and the suffix. But I like to add into this another locant and a suffix stopper. For whatever reason, a year ago in my OChem 2 class, I was teaching this stuff around Thanksgiving time, and I kept calling it a stuffing stopper. Maybe it was, yeah. I guess you got 2 types of stuffing. Yeah, anyways. Okay. Stocking stuffer. But I was thinking of stuffing, like Thanksgiving stuffing side. Anyways. The prefix, I think you guys have all gotten pretty familiar with. These are the substituents on the chain and their locants. So something like saying para-bromo-nitro, that's the prefix, benzene is the root. Or saying 3,3-dimethyl, that's the prefix. The root, I think you guys have all gotten pretty familiar with. Longest carbon chain with the principal functional group, or the primary functional group. What's the difference? Principal and primary? Which one?
More conjugated, it's more
Principal is more aesthetic or primary? One of them is. I'll let you decide. Now, when we talk about this locant, we're just saying that it describes where the suffix is, or the suffix stopper. And the reason that I show it to you like this is actually because I didn't come up with this. I took this from Ron Valcarce's class, and it is how IUPAC idealizes their names. You should have the root, pent, hex, but, and then a number describing where along the chain that functional group is. Pent 1-ine, hex 2-ene, butane, because you don't need to describe where the alkane is. All right, so the fun stuff is all right here. The suffix and the suffix stopper. Can you guys tell me suffixes? Can you guys tell me what the suffixes are? Nope. Those are the stoppers. The suffixes are only hydrocarbon based. Ane, ene, ine, and enine. That's your suffix. Full stop. Your compound must have a suffix based on its functional group. And if there is no alkene, if there is no alkyne, then it's always alkane, even if technically there is no alkane. For instance, a compound that was just reported this year, which is kind of crazy because it seems like a simple compound, but it's actually very energetic. It's hard to make. This has a name, methane tetrol. Where's the alkane functionality? There is no CH bond in the whole molecule, right? So where's the alkane? It's an sp3 hybridized carbon, so that is the root. And the suffix is that's the suffix. And the suffix stopper is OL. So, suffix stoppers by order of priority. Do you know the highest priority suffix stopper? The highest priority principal functional group. Not alcohol. That was OCHEM 1. Carboxylic acid. If we have the time, my watch is dead. What time is it? No, maybe we won't get through all of it. Carboxylic acid, which as Neira said, gives us oic acid, except for in common names where it gets the suffix ic acid, or sorry, the suffix stopper, ic acid. This is why I call it a suffix stopper. You're going to have ane oic acid, ene oic acid, or ine oic acid. But it is important to realize that if you have a stopper, you cut out that last ene. Do you notice how down here, ene was stoppered by ine, and the e of ene got cut out from ene to make space for ine. So when you add a stopper, you take off that e, unless you add a multiplier like di, tri, or tetra, and then that e comes back in. I don't know, because I'm not a linguist person. I'm not a linguistic. What's the word here? I'm not a linguist. And I don't know that IUPAC consulted with linguists when they made these rules, but I think it's about how it rolls off the tongue. You don't want to have vowels next to each other, and you don't want to have consonants next to each other, so you can remove or replace that vowel when you need to. Okay, I think we're pretty much out of time. I don't know how, I'm not going to give you guys a lot of things on your exam, you're going to get esters, which end with O8 or 8 if it's common. You're going to get ketones, which gets -one. You're going to get aldehydes, which gets -al. And then we get back to OCHEM 1. If you get alcohol, you get -all. Where we'll pick up is how do we name aldehydes and ketones as substituents, and how do we decide on the priority? I should have actually written this differently. Oops. Now that you all finished it, these are both the same priority, and in the event of a tie, you give to the lowest locant, which is always an aldehyde. The aldehyde will always be at position 1, and the ketone will never be at position 1, so a tie goes to the aldehyde. So we'll do some practice with nomenclature when we come back, yeah? And we'll finish the rest of our list. Okay? Have a good night, guys. I hope you can make it to that review session on Thursday. And otherwise, I'll see you on Thursday for our last class. Okay? Have a good night.